So, hello everybody. Let's continue again our lecture 11. Today I would like to teach you about still in the scope of mechanics of materials. And let's see the full screen first. Okay. So, today is about mechanics of materials, but it's about the stress strain load on the axial loading type. Do you know what is stress? I think you may already learn last time already. Stress is just a force over by the area, or on the other hand, this is if force over by area means the distribution of the force to that area is equal, so it's uniform distributions. But the stress itself sometimes is not really uniform distributed, means the stress is just the force in the particular very small area in each area. Yeah. So next is the strain. Have you heard of the strain? The strain is just the deformations of the materials, and the deformation in this case is in the percentage, not percentage but ratio. So the strain, you will see the formula later what is this about. So the stress strain and axial loadings. So in this case we will learn about the stress strain relationship by the axial loading only. So we have the loading in the axial directions. Let's lead it through. The suitability of the structure or machine may depend on the deformation in the structure as well as stress induced under the loadings. The static analysis alone is not sufficient. Okay, so sometimes our machines is not only maybe you have heard about the word rigids that I often use in the previous chapter, in not previous chapter but the last few chapters in the statics. The rigid body, you remember what it is? Rigid body means there is no deformations even though we put the force onto the objects. But in this case, in some case, the deformation is matter. Okay, so in this case, in this chapter, we will talk about the deformable bodies. Yeah. Okay. So next, considering structure as deformable allow determination of the member force and reactions which are statically indeterminate. And the determination of the stress distribution within the member also required to consider the deformation in the member. So you will see that in each stress distribution in the formula or in the problem, we will see each member of the structures also deform. And this chapter is not chapter 2, my bad, it's chapter 11, is concerned with the deformation of the structure member under the axial loading. The later chapter will deal with the torsion and pure bendings. So in this case we will talk only about the axial loadings. Normal strain. So this one we will explain about the strain. What is it? Oh, sorry. Okay. If we have this rod which is fixed on this ground, this is a picture A. Okay, this is origins, And this one is deformable objects, means when we put the force P, we will have these deformations. Yeah. And this is the unit is, if it SI units, it will be in meters. Okay. So again, in the original state, it has a length L. Okay. The length is L, but then when on a picture B, the length is not L anymore because of course we have lengthening it. So we have L plus the deformations. Okay. And here the formula below shows the stress and the strains. This is what we call strain, this epsilon, and then we have the deformation here, and you can see the strain is the deformations divided by original length. So the strain itself is really in ratio of the deformation to the original length. Okay. And here are both also the stress. We already talked about this. So next pictures. So what happens if we have double of the area and double of the force P? We will still get the same deformations. Deformation is still the same. Okay. What if we have double length L2, but we have the same area here, and then we have the same P? We will have double deformations. Okay. So means the deformation of the object is also depend on the length of the object. If everything is the same, force the same, the area is the same, then but we have double of the length, means we have double of the deformation also, right? But as you can see, the strain is still the same. The reason is the strain is just the ratio of the deformation between the deformation and the original length. So, and this is also, what is the deformation then? When you apply the force P here, as the last chapter I already explained, if you cut anywhere on the object, you still see force P applied on it. So every point you cutting the objects means you have force P. Then what does it mean? When I cut this kind of rod into small pieces, okay, and these pieces, for example, if the length L have this 100 pieces, each pieces is deforming as this deformations length. And if I double the length, means I have another 100 pieces here. Then I have also additional deformations to this object. That is why when we have double of the length, we always have double of the deformations. Okay. So next is the stress strain test. As I mentioned to you before, normally the strength, last time we learned about the strength of the material, right? Then this time I will tell you how the strength coming from. Actually, it's coming from this kind of test. Of course, there's variety of tests, but this is the standardized one. So we have we have a materials here as a rod, okay, and then we fix those two and okay. For example, I have a kind of steel, okay, and this is what we call a steel. And then someone asks me, hey, can you analyze the stress strain curve or also the material strength of this steel? What I do is I will grinding or machining, means I change the shape of this rectangular here into what like this, okay. So I will get into the big machine to change this shape into this shape, yeah. And then when I got this things, and then I will put it in to the test bench. This is what we call test bench. It's just the test machine, yeah. I put it in, I squeeze it through because we have a thread here, bottom and the end, and then I screw it into the top and the bottom as I said before, and then the test is start. What did this test do is they're just recording, they are pulling the force. They have force P, for example, they start pulling these materials, and then they also measure how much is deformed, yeah. And then in the end they will plot the curve of P and deformations, right? They will have, for example, at the deformation of 0.1 millimeters, you will use force of 500 newtons, okay. And then in the next point, actually there will be a lot of measurement point like this, for example, and then until it break here. This is the material is broken, or we say ruptures, okay. And then you know that when we have a P here, we can change it to stress. How do we change it? You remember already, right? So we have P over A, and then we know already what is our diameter here, yeah. We know the diameter of this rod already, so we can just plug in, we can just divide these forces by the area of this kind of rod material here, yeah. What about these deformations? How do we change it? So normally we will not read as a deformation in millimeters, but we will use strain. What is the formula for the strain? Is deformation divided by L, right? So we just divide it by the length here, L, and then we got the strain. But actually it's a little bit more complicated, because we have also this length, we have also this 1 and 2 and 3. The formula is a little bit more complicated for the strain, but actually out of this we can creating the stress strain curve. And then you know, in this max point here, the max point here where the force is highest, we call this the material strength. or we call ultimate tensile strength. Okay, at this point, yeah. So here is what is similar to what I have shown. So actually, for example, low carbon steel. So normally, in the steel we have high carbon or low carbon. When we have higher carbon, we have more hardenings. For example, maybe I explain the curve first. This one is what? The stress and the strain, and then we got it by previous test as you've seen. When we have low carbon steel, we will have a little bit ductile. What is ductile? Ductile materials. This stress strain diagram for ductile materials. Ductile means like a chewing gums. Can be, for example, this is the first stage when you're pulling, yeah. And then in the second stage, when you're pulling, you have a kind of bucking because it's have a very large deformation here. So you can see that here the strain of these materials can deform up to 25%. It's quite ductile here, yeah. Comparing also to the aluminum alloy, also 20%, 0.2. It's also quite high. The material can deform itself by 20% or 25% until it ruptures here. Okay, it's quite high. And okay, let's list this graph first. So starting from this point, and you can see that from the start, you pulling these materials, yeah? You pulling this material A, and then until it's got the deformation of 0.1%, you can see here, and it's dropping down. This is the material mechanisms. That's why we call mechanism of materials, how material works, how material have relationship between the stress and the strain. And then when you reach this certain stress, you will get a little bit lower of the stress here, and then it get deformed. And then until it deformed by 0.02 or 2% of deformations, then we will call this yield strength. Okay, and then this is where we have maximum of the stress. We call this ultimate tensile strength. Okay, and then here is where we have ruptures or breaking of materials. Alright, so here also the same, into the same principle. Okay, so we have until it yield, and then till it ruptures, and then here is the ultimate tensile strength. Okay, and then we have brittle materials. You can see how sharp at this breaking. It's quite sharp comparing to the previous picture, right? You can see previous picture is quite have some shape blocking like this, yeah, until it's break. So here is the picture as B, as the ruptures here, as a circle. Okay, so this in this ductile material is quite deformable. It's deformed really high. It can deform up to 20%, 25%. But you can see brittle materials here. Actually, if you see at this point, it's quite small comparing to 20%. I doubt that it's deformed until 1%. Yeah. So you can see the sharpness of the break position is quite sharp. But on the other hand, if we plot previous plot and to this plot, I will just show you a little bit. So this is what we call ductile material. This is brittle. Brittle is like glass, for example, but this is actually not a glass. It's quite not deformed that much, but it has higher strength. Normally, it has higher strength until it breaks. You can see ductile materials, the material strength is around here. It's quite small comparing to the upper one, but it can deform quite large. Compared to this brittle materials, the deformation is not that high, but they have higher ultimate tensile strength. Okay? So, then just now comparing, here is what we call Hooke's law. What we are learning so far, here, the stress and strain, and here Hooke's law, modulus of elastic. What is elastic zone? The elastic zone is this zone, because, for example, if I draw this graph, okay, and when I just deforming this one until, for example, if this is U point, so this U, this is where I stressing these materials, and then when I remove the force, for example, it will go back to the original state because it's still in the elastic zone. Here is elastic zone. Elastic means when it deforms, it will shrink back to the original state. And then why do we call it yield here? So the yield is that when you reach this point, it will come back to another path here. And then here you have R 0.2, means you have deformation of the deformations, permanently deformations by 0.2%. This is what we call yield point. Yeah. So until more than this point, we call plastic zone. Plasticity here means we have permanent deformations more than 0.2% of materials. Here is what this zone, yeah. So means in this, again change the color to green, in this elastic zone we use also Hooke's law. So they will find this slope K and then call it E. So it here Young modulus or modulus of elasticity. So we can predicting the deformation of the material itself. Yeah. So coming back to this graph here, So we have different materials. The pure ions, yeah, have really low strength comparing to the others. When we add the carbon into this pure ion, then we get carbon steel, so we have a little bit higher strength. And then we have high strength low alloy steel here, yeah. So we add also alloy. Alloy is the other composition which is not carbon into the steel to make it has more strength. And then we are quenching, tempering this one. What is this one? Oops. Oh, what happens? No. Okay, so when we have quenching here, yeah, what is quench? It means we have heat treatment. To make an example, do you know, have you ever seen the, maybe in the movie, some Japanese movies, when they make a sword, yeah? When they make a sword here, like this, Japanese sword, for example, a little bit ugly here. But when they're forking it, you know, they have to, how to say, make a material super hot, right? It make material super hot, and then the material is become red, yeah. Red mean the material is quite hot, and then after that they just put this hot sword into the cool waters. To lowering the temperature is quite fast. This is in the today words called quenching, yeah. We do the quenching because we would like to have a materials have different microstructures. We will have microstructures that is favoring the strength. We will have more strength if we how to say, if we put this, for example, if I have a kind of materials, yeah, normally is normal steel, for example is low alloy steel, but then you put this into very hot temperatures, for example 1000 Celsius, yeah, it's become super hot here. And then after that you put this into lower than maybe about 20 degrees Celsius, very fast. It has to be very fast, then we call it quenching. And then these materials will have higher strength, as you can see here, yeah. Mean in this case, in the real world, if that's why the steel that has higher strength in the real world is more expensive than the other one, because you require the additional process to tempering this materials and then cool it very fast. And this process is quite expensive. We call it heat treatment, yeah. Okay, this is one of the strengthening process we have. Another one, oh, maybe I can search for you. We can also strengthening material by short pinning. Here also one of the method to have a higher strength on the materials. Let's see. You can see that the short pinning is, for example, when I have this materials, I will use really small ball to shooting on the material itself, and then make material deform like this middle pictures here. So when you have the deformation on the surface of the materials, it's kind of increasing the strength of the material itself. So this is what we call sharp pinnings. So we have materials, then we shooting 1,000 and 10,000 of ball into the materials. So for example, I may write pictures. We have a material like this. We have a gun, I don't know, kind of gun, and then we shooting really small, really small ball to these materials and deform the surface of the material like this. And then this kind of deformation here causing the residual stress. You may also search. Maybe, yeah, I will explain it later then. The residual stress is just the stress remaining in the materials causing by the plastic deformations. Yeah, and then this kind of residual stress help the material to have higher strength. Okay. All right, then going back to our original things, we have this. Remember again, this one is Hooke's law, yeah, modulus of elasticity, and this is Young modulus, and this one is the slope here, the slope of this material when they are still in the elastic zone. Okay, then next, okay, as I mentioned to you, that we have this kind of we call this elastic zone, and this is plastic zone. Yeah, so mean if the strain disappear when there is a stress is removed, the material said to be behave elastically, and the largest stress for which this cause called elastic limit means the stress that is starting to have the plastic deformations, we call it elastic limit. Yeah, when the strain does not return to zero after the stress removed, the material said to behave as plastically. Okay, this is what I have explained in the previous page. And fatigue, this is really important in real life, because this is the most important topic for the strength for the automotive industry. What is fatigue? So the fatigue is a member that fail by the many lot of cycle. For example, okay, do you have can, and this is just the thing that you pulling this out, right? Then you can bending it couple of times and then it will loose off. So means it will not break for the first time, but it needs cyclic load to apply onto the materials until it's break. And this is all the same. For the fatigue, it means the material is not break by only one time force. For example, 50 newtons, you apply the tension onto the materials. It will not break for the first time, but it might break when you apply it and then release it, apply it, release it for example, 10,000 cycles. If I writing this to be more pictures here. So when we have force 50 newtons, and then this is kind of plot for the force. I apply the force here 50 newtons, and then I release the load down. Yeah, this is what we call one cycle. We have to apply the force and release the force, and then I apply the force, release the force, apply the force, release the force for 50 newtons. For example, for 10,000 cycles. And then at this 10,000 cycle is break. Mean this material is breaking by fatigue itself. Okay? Means, for example, these steel materials have this kind of strength. When you applying a load of 40 ksi, it will break at 100,000 load. If you apply it as 35 newtons, it will break around 1 million cycle load. And this curve is the stress to the cycles, yeah? And this curve for the fatigue always plotted in log normal graph. What is log normal? You can see on the x-axis is a log graph, so it's increased by 10-fold, and then for the stress is normal. So logs mean you have a log on the x-axis. Normal mean you have normal graph on the y-axis. Okay, and you can do this experiment by yourself also. Yeah. Do you know the clip here like this? Okay. You bending this clip, for example, 30 degrees up and down, how many cycles you get? And you do another, you get another clip, do again, but this is maybe 60 degrees. You will see a lot of difference in cycle, I promise you. This will not 2 times cycles. For example, if you breaking this top one, you use 100 cycles to break. This one will not be 50, as the angle is 2 times higher, but the cycle is not 2 times lesser. This will be much less, maybe 20 or 25. Just fine if you want to. Then you learn about the fatigue. The fatigue cannot be plotted on the normal graph. It has to be plotted on log normal. Okay, so deformation under the axial load. Okay, when we have this, we have a hook loss. So remember this, and this hook law also can be transformed to this kind of things. It's a deformations, and this deformation is depending on force, area, and the Young modulus. Okay. All right. So let's see. Then this strand, no, this the strand, not deformations, and then this strand is the deformation over IL. So in the end, you can also got the deformation by this formula. Okay, but with the variant of loading, cross section, and the material properties, you can also use this formula also. For example, you have different area, different force in each point of the bodies. Then you have to use sigma PL over area and Young modulus. So I will show you in this example. Okay, so next is, so determines the deformation of the steel rod shown under the given loads. So we given the Young modulus, and also we have the diameters, the big diameters here, and we have no, this one is small this one is small diameters, and this one is big diameters. Okay. So let's start. So in this case, first you have to know that we have 3 sections. Okay, write this. We have 3 sections. We have this. So we have this section. This section and these sections. So okay, then we will solve this problem together. So we start with this first sections. When we cut through the first section here, why we have to cut? So that we can write the force that is applying to this rod. Okay, so we have 30 KIPS, and this is also P3, P1, I would say P1, and then we know that our P1 is equal to 30 times 10.3 LB. Okay, and then next is the section 2. If we cut through the section 2, we know that we have this kind of force, and then we have this also, this force and this force, 30. This is 45, and then you know that this P2 is just the 45 minus by 30, but in this case it will be negative because it's on the negative side. It will be negative 15. And then last but not least, this one, we have this three forces. So what do we have here? Then we have V3 as 75 plus 30 minus 45 time, and is equal to 60. Okay, Then now you know each and every point on those lengths, yeah? Then what is the length for 1 here? Length 1 here in the pictures is 16 inch. Length 2 is equal to 12 inch. Length 3 is equal to 12 inch. Yeah. And the area 1 is equal to pi. Here the small diameter is 0.618 divided by 4 is equal to 0.3 inch square. And area 2 also the same principle. We have 0 over 4 is equal to 0.9 inch square, and area 3 is equal to also 0.9 inch square. Is okay. Then in this case we would like to find the deformation, right? And our deformation formula is sigma pi and ai. You can see that for the P we know already for all the points. For L we know already. For A area we also have it on the right side. For elastic for the Young modulus we also have this one. So we can already finish this problem. So we have 1 over 29 10 to the power of 6. This one is Young modulus. Everything in the material for the whole thing is the same, so we don't have to differentiate that. So this one, and then we multiplied it by this one is 60 as P. Maybe we start with P1 30 times Li. L1 is 16 over 0.3 plus minus 15 over 0.9 plus 60 over 0.9, and then you will get 75.9 10 to the power of minus 3 inches. So means this thing will deform it by 75.9 10 to the power minus 3 inches. Yeah. Okay. Let's continue next time.